Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the depths of space, where an enigmatic visitor has left astronomers scratching their heads in the most delightful way. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On a quiet night in January 2019, the Atlas telescope system in Hawaii turns its mechanical eye toward a patch of sky that appears, to most observers, utterly unremarkable. The dome rotates with the patient precision of centuries, following patterns established long before any human walked upright on distant Earth. Stars wheel overhead in their ancient configurations, each point of light carrying stories written in wavelengths and spectra, in the subtle mathematics of distance and time. The twin Atlas observatories, one nestled on Mauna Loa's volcanic slopes, another perched on Haleakala's dormant crater rim, operate with the methodical dedication of automated sentinels. Their wide-field cameras sweep the sky in overlapping patterns, photographing the same stellar fields night after night with the persistence that only machines possess. Each image captures roughly 15 square degrees of sky, an area equivalent to 30 full moons laid side by side across the celestial sphere. The cameras themselves represent decades of technological evolution. Their charge-coupled device sensors capable of detecting individual photons that have traveled across interstellar distances to reach these volcanic peaks. The volcanic rock beneath these telescopes holds memories spanning millions of years, layers of basalt and ash that chronicle the Pacific Ocean's slow dance across tectonic plates. Each eruption that built these islands recorded the chemical signature of mantle material drawn from depths measured in thousands of kilometers, creating a geological archive that extends back to epochs when these islands existed only as underwater seamounts. Yet the telescopes themselves concern themselves with far more ancient histories, scanning for objects whose origins predate not only the Hawaiian Islands, but the formation of our solar system itself. The Atlas project emerged from a simple recognition: space contains objects capable of ending civilization, and humanity's survival depends partly upon detecting them before they detect us. The system searches primarily for potentially hazardous asteroids, those rocky remnants of planetary formation that follow orbits capable of intersecting Earth's path around the Sun, night after night. The automated survey accumulates images with the methodical patience that characterizes all successful astronomical endeavors, comparing each new photograph against previous observations to identify anything that moves against the stellar background. But tonight, something moves against this stellar backdrop that doesn't belong to the familiar choreography of planets and known asteroids. The telescope sensors register a faint smudge of light, no brighter than thousands of other celestial objects catalogued each evening. Yet this particular smudge carries with it the signature of motion, not the predictable elliptical orbit of a solar system resident, but the hyperbolic trajectory of something that has never felt the sun's gravitational embrace as anything more than a temporary perturbation. The detection unfolds through the accumulated weight of digital precision. Charge-coupled device sensors convert individual photons into electrical signals, each pixel recording the subtle variations in brightness that distinguish moving objects from the stellar background. The process involves capturing multiple images of the same sky region, separated by intervals of minutes or hours, then using computer algorithms to identify objects that shift position between frames. Software compares successive images with the mathematical patience that characterizes all modern astronomical survey work, flagging anomalies for human review with the quiet efficiency of well-designed automation. The initial measurements reveal an object moving at approximately 44 kilometers per second relative to the Sun, a velocity that immediately distinguishes it from the asteroid population that typically travels at speeds closer to 20 kilometers per second. This excess velocity carries profound implications, suggesting an object that originated far beyond the gravitational influence of our solar system. In the realm between stars, where the Sun's gravity becomes indistinguishable from the cosmic background, the discovery itself emerges not as a moment of sudden revelation, but as the gradual recognition of pattern within apparent randomness. Numbers appear on computer screens in observatory buildings scattered across continents, brightness measurements, positional coordinates, spectroscopic data that accumulates with the methodical persistence that marks all astronomical endeavor. Each data point represents hours of telescope time, careful calibration of instruments, and the patient work of reducing raw observations into scientifically meaningful measurements. Confirmation requires multiple independent observations from different observatories, each measurement adding precision to the object's calculated trajectory. The Minor Planets Center in Cambridge, Massachusetts, serves as the global clearinghouse for such discoveries, collecting observations from astronomers worldwide and publishing orbital elements that allow other researchers to point their telescopes toward this newcomer. Only through such collaborative effort does the astronomical community build confidence that this faint smudge of light represents something genuinely extraordinary. This visitor receives the designation 3I/Atlas, the third confirmed interstellar object to grace our solar system with its presence. The notation sits quietly in databases and research papers, a simple alphanumeric string that conceals one of the most perplexing mysteries modern astronomy has encountered. The 3I prefix indicates its interstellar origin, placing it in the exclusive company of 1I/Oumuamua and 2I/Borisov, those earlier cosmic tourists whose brief visits rewrote textbooks and challenged fundamental assumptions about the nature of small bodies in space. The name itself follows the conventions established by the International Astronomical Union for designating interstellar objects. The Atlas portion honors the telescope system responsible for its discovery, linking this mysterious visitor forever to the volcanic peaks of Hawaii where human ingenuity first recognized its presence. Such nomenclature creates a permanent connection between cosmic wanderer and terrestrial discovery, embedding the story of detection within the object's official identity. Yet even among this rarefied company of interstellar wanderers, 3I/Atlas stands apart. Where Oumuamua displayed the elongated profile of a tumbling space needle and exhibited mysterious non-gravitational acceleration, and where Borisov behaved with the predictable dignity of a well-mannered comet, complete with coma and tail. This latest arrival seems determined to confound every attempt at classification, every theoretical framework constructed to explain the behavior of objects born beyond the gravitational embrace of our Sun. The early observations reveal motion consistent with a trajectory that originates far beyond the heliosphere, that tenuous bubble of charged particles that marks the boundary of solar influence. This object has traveled through the vast emptiness between stars, crossing distances so immense that even light, traveling at its cosmic speed limit of 300,000 kilometers per second, requires years or decades to traverse similar spans. It arrives in our neighborhood like a messenger from realms that exist only as mathematical abstractions in stellar evolution models, carrying within its composition the chemical signatures of stellar environments that formed when our galaxy was younger by hundreds of millions of years. The interstellar medium through which 3I/Atlas has journeyed represents one of the most hostile environments imaginable, a near-perfect vacuum punctuated by perhaps one hydrogen atom per cubic centimeter, swept by cosmic rays and the stellar winds of distant suns. The temperature hovers just a few degrees above absolute zero, creating conditions where most familiar chemical processes cease entirely, for eons uncounted. This object has tumbled through such emptiness, its surface sculpted by micrometeorite impacts and the slow erosion of high-energy radiation. The fact that anything coherent survives such a journey speaks to the fundamental resilience of matter organized into planetary-scale structures. Yet, from the very beginning, 3I/Atlas refuses to behave according to the scripts written for interstellar visitors. Its light curve, the pattern of brightness variation as it tumbles through space, displays characteristics that fit neither the profile of a typical comet nor the expected signature of a rocky asteroid. The object brightens and dims in ways that suggest internal complexity hidden beneath its unremarkable surface appearance, as if the very act of observation reveals new layers of mystery rather than providing the anticipated answers that usually emerge from careful astronomical study. Telescopes around the world begin their patient vigil, tracking this cosmic wanderer as it follows the mathematical certainties of orbital mechanics while simultaneously displaying properties that challenge those very same physical laws. The Hubble Space Telescope, Spitzer Space Telescope, and ground-based observatories from Chile to California join the observational campaign, each instrument contributing unique capabilities to the growing dataset. Each night of observation adds another layer to the enigma, another data point that refuses to align with existing theoretical frameworks developed through decades of studying solar system objects. The accumulated weight of measurements creates not clarity, but an ever-deepening appreciation for how little we truly understand about the objects that drift between the stars. Every new observation seems to raise more questions than it answers, suggesting that 3I/Atlas represents not simply another interstellar visitor, but something that challenges fundamental assumptions about how such objects should behave when they encounter the inner regions of our solar system. The universe, it seems, has sent Earth's astronomers a puzzle wrapped in the deceptive simplicity of reflected sunlight. And the more carefully they look, the more questions emerge from the darkness between the stars, each observation revealing new aspects of a mystery that grows more profound with every passing night, every additional measurement, every attempt to categorize this enigmatic wanderer according to the familiar patterns established by countless previous astronomical discoveries. The first detailed observations of 3I/Atlas arrive like whispered secrets from the darkness beyond Pluto's orbit, carrying with them the accumulated photons of a journey that began in realms so distant that our entire solar system would appear as nothing more than a faint speck against the cosmic background. Astronomers trained their instruments on this faint point of light, expecting to decode its nature through the familiar language of reflected sunlight and spectral analysis that has served science faithfully for more than 2 centuries. Yet the data that emerges from these initial studies carries an undertone of cosmic mischief, as if the universe has decided to present Earth scientists with a riddle wrapped in the mundane mechanics of orbital dynamics. The object moves through space with the mathematical precision that governs all celestial mechanics, following a hyperbolic trajectory that curves gently around our sun before heading back toward the interstellar void from whence it came. Its path carries the unmistakable signature of gravitational influence, the elegant arc that results when a massive star bends space-time itself, guiding wayward objects along predetermined routes calculated with the same geometric certainty that governs falling apples and orbiting planets. The mathematics involved speak to fundamental principles established by Newton and refined by Einstein, equations that describe how matter moves through the curved geometry of space and time. Yet within this predictable framework of gravitational physics, 3I/Atlas displays characteristics that refuse to conform to the established categories that have served astronomy faithfully since the dawn of telescopic observation. The object seems determined to occupy a liminal space between the well-understood behaviors of comets and asteroids, exhibiting properties that belong partially to both classes while conforming completely to neither. Initial brightness measurements reveal an object that varies in luminosity over time, periods measured in hours, suggesting rotation as it tumbles through the vacuum with the slow dignity of something untethered from planetary gravity. This tumbling motion should provide direct clues about the object's shape, density distribution, and surface properties through the time-honored technique of photometric analysis. Asteroids typically display regular brightness variations as their irregular shapes present different cross-sectional areas to observing telescopes, creating light curves that rise and fall with the mathematical predictability of rotating geometric solids. Comets, by contrast, often maintain more stable brightness levels as their spherical nuclei remain hidden within expanding clouds of sublimated gas and dust that scatter sunlight in all directions. The brightness of an active comet depends more upon the rate of outgassing than upon simple geometric effects, creating light curves that reflect the complex interplay between solar heating, subsurface ice distribution, and the physics of sublimation in near-vacuum conditions. But 3I/Atlas presents a light curve that fits neither pattern precisely, displaying characteristics that seem to borrow elements from both while adhering completely to the expectations of neither. The brightness variations occur with a periodicity that suggests rotation, approximately 2.5 hours for what appears to be a complete rotational cycle. Yet the amplitude and character of these changes hint at something far more complex than simple geometric effects alone could produce. The object brightens and dims in ways that seem almost deliberate, as if its surface contains regions of dramatically different reflectivity arranged in patterns that defy easy explanation through conventional models of small body formation and evolution. Some observations suggest brightness variations that exceed what could reasonably be expected from shape effects alone, implying either extreme elongation, making 3I/Atlas one of the most stretched objects ever observed, or surface features that reflect sunlight with dramatically different efficiencies. Spectroscopic analysis, that fundamental tool of astronomical investigation that allows scientists to decode the chemical composition of distant objects through careful study of absorbed and reflected light, yields results equally perplexing and frustrating to researchers accustomed to clear answers. When starlight reflects off an object's surface, it carries with it the chemical fingerprints of whatever materials compose that surface, creating absorption features at specific wavelengths that correspond to known atomic and molecular transitions. Iron-rich asteroids display characteristic absorption features in their reflected spectra, revealing the presence of olivine, pyroxene, and metallic iron through well-understood spectral signatures. Ice-dominated comets reveal the signatures of water vapor, carbon dioxide, methane, and complex organic compounds as these materials sublimate under solar heating and create absorption features in both reflected sunlight and thermal emission. The technique has proven so reliable that astronomers can determine the composition of objects billions of kilometers away with greater precision than early chemists achieved for terrestrial samples. The spectrum of 3I/Atlas appears remarkably featureless across all wavelengths where observations prove possible, displaying an almost flat reflectance that varies little from ultraviolet through near-infrared wavelengths. This spectral neutrality suggests either a highly unusual surface composition, unlike anything commonly found among solar system objects, or perhaps a covering of material that has been processed by cosmic radiation and micrometeorite bombardment during its interstellar journey to the point where diagnostic features have been erased entirely. Such spectral flatness proves deeply frustrating to researchers accustomed to reading cosmic chemistry through the subtle language of absorbed and reflected light. The object seems determined to conceal its composition behind a veil of uniform reflectivity that offers few clues about its formation environment or evolutionary history. Every attempt to match the observed spectrum against laboratory measurements of known materials yields ambiguous results that suggest either exotic compositions or familiar materials altered beyond easy recognition. Professional astronomers share their puzzlement in conference presentations and research papers, describing observations that consistently fail to align with theoretical expectations developed through decades of studying solar system objects. The language they use in technical publications carries the particular frustration reserved for phenomena that resist classification despite increasingly sophisticated observational techniques. Terms like anomalous, unexpected, and inconsistent with current models appear frequently in their descriptions. Academic euphemisms for the more direct admission that nobody quite understands what they're looking at. The astronomical community responds with characteristic thoroughness and international cooperation, organizing observing campaigns that will track 3Y/Atlas throughout its passage through the inner solar system over the coming months. Telescopes across 6 continents coordinate their efforts through formal agreements and informal collaborations, creating a global network dedicated to monitoring this enigmatic visitor with unprecedented precision and temporal coverage. The Hubble Space Telescope dedicates precious observing time, currency more valuable than gold in the astronomical community, to obtaining high-resolution images that might reveal surface features invisible from ground-based observatories. Radio telescopes spanning continents listen for any emissions that might reveal active processes occurring on or near the object's surface, searching for signals that could indicate everything from electrical activity to outgassing events too subtle for optical detection. The European Southern Observatory redirects multiple instruments at the Very Large Telescope Complex in Chile, while observatories from Hawaii to the Canary Islands join the coordinated effort. Each facility contributes unique capabilities. Some excel at photometry, others at spectroscopy, still others at thermal observations that reveal surface temperatures and thermal inertia. The combined dataset promises unprecedented coverage of 3I/Atlas across multiple wavelengths and observational techniques. Each new observation adds layers of complexity rather than providing the anticipated clarity to the emerging picture of this interstellar visitor. The object's behavior seems almost calculated to confound every attempt at easy categorization, displaying just enough characteristics associated with known object types to encourage theoretical models, while simultaneously exhibiting properties that violate the fundamental assumptions underlying those very same models. It displays some characteristics historically associated with comets, particularly its brightening as it approaches perihelion and shows evidence of material loss from its surface, yet lacks the obvious coma and tail structures that mark active outgassing in conventional cometary objects. It shows some properties typical of asteroids, notably its apparently rocky composition suggested by thermal observations and its general lack of obvious volatile activity, yet exhibits brightness variations and subtle trajectory modifications that challenge purely asteroidal explanations. The scientific method demands that researchers consider all possibilities systematically, including those that stretch the boundaries of conventional understanding and challenge theoretical frameworks that have served successfully for decades. Could 3I/Atlas represent an entirely new class of interstellar object, something that previous theoretical models failed to predict because they focused exclusively on objects formed within our own solar system? Might it be composed of materials genuinely unknown within our local cosmic neighborhood? Substances that formed under the exotic conditions found near different types of stars with dramatically different chemical abundances. These fundamental questions multiply faster than definitive answers emerge from the steadily accumulating observational data. Each measurement that should clarify the object's nature and place it confidently within established taxonomic categories instead reveals new aspects of its perplexing character. new properties that fail to align with any single theoretical framework. The universe has presented Earth's astronomers with what amounts to a cosmic Rorschach test, an object that seems to reflect back whatever expectations they bring to its study, while simultaneously confounding those very same expectations through subtle violations of predicted behavior. As 3I/Atlas continues its stately progression through the inner solar system, following the gravitational choreography that governs all celestial motion, it carries with it the accumulated frustrations and fascinations of an entire international scientific community. Here moves an object that embodies the fundamental mystery of existence beyond Earth, the humbling recognition that the cosmos contains phenomena that persist in challenging human understanding. Regardless of how sophisticated our instruments become or how comprehensive our theoretical models appear, the traditional binary classification that has served astronomy faithfully for centuries begins to crumble under the weight of observations that refuse to conform to established patterns with the quiet persistence of water wearing away stone. For generations stretching back to the earliest telescopic observations, the distinction between comets and asteroids has provided a reliable conceptual framework for understanding the diverse population of small bodies that populate our solar system. Comets, conceived as dirty snowballs that develop spectacular tails when solar heating sublimes their icy surfaces into brilliant displays visible to the naked eye. Asteroids, understood as rocky remnants of planetary formation that remain largely unchanged throughout their cosmic lifetimes, preserving in their crystalline structures the chemical signatures of the solar nebula from which planets condensed. This elegant dichotomy has guided spacecraft missions worth billions of dollars, shaped theoretical models that describe the formation and evolution of planetary systems, and formed the intellectual foundation for countless research papers published in journals spanning decades of astronomical investigation. The classification scheme seemed robust enough to encompass virtually any small body that future observations might reveal, providing scientists with a reliable taxonomy for organizing their understanding of objects ranging from Earth-crossing asteroids to long-period comets arriving from the distant Oort cloud. 3I/Atlas arrives in our solar system seemingly determined to demolish these comfortable categories through the quiet persistence of contradictory evidence that accumulates with each passing day of observation. The object displays none of the obvious coma or tail development that marks classical cometary activity, visible even through modest amateur telescopes. Yet it brightens dramatically as it approaches the sun, in ways that suggest significant amounts of material are indeed leaving its surface through processes that remain frustratingly invisible to direct observation. The complete absence of a detectable coma proves particularly puzzling to researchers who reasonably expect interstellar objects to contain significant amounts of frozen volatiles accumulated during their extended journey through the cold vacuum between stars. Theoretical models developed over decades of studying solar system formation predict that objects formed in the outer regions of planetary systems should retain substantial inventories of water ice, carbon dioxide, methane, and other compounds that remain frozen at the temperatures characteristic of interstellar space. During the eons-long journey between stars, such objects should accumulate additional volatile materials through direct condensation from the sparse interstellar medium, gradually building up surface layers enriched in substances that would sublimate readily when exposed to solar heating. Most computer simulations suggest that interstellar visitors should outgas vigorously upon entering the inner solar system, creating the characteristic fuzzy appearance and extended tails that distinguish active comets from inert asteroids through even rudimentary telescopic observation. Yet even as 3I/Atlas approaches to within astronomical unit distances of the Sun, regions where water ice should sublimate at rates sufficient to create obvious coma development, it maintains the sharp, star-like appearance of a perfect point source, indistinguishable from background stars, except for its motion against the stellar field. The object's apparent refusal to develop visible outgassing signatures challenges fundamental assumptions about the composition and behavior of interstellar matter. High-resolution images obtained through dedicated observing programs using the Hubble Space Telescope reveal absolutely no hint of the surrounding cloud of gas and dust that typically envelops active comets even during their earliest stages of solar approach. The telescope's remarkable optical systems, capable of detecting coma development at levels far below the threshold of ground-based observation, show 3I/Atlas as nothing more than a simple point of light, whose brightness varies with the mathematical precision expected from a rotating solid body. This complete lack of obvious cometary activity suggests either that 3I/Atlas contains remarkably little volatile material despite its interstellar origin, or that some currently unknown mechanism prevents normal outgassing processes despite solar heating that should inevitably trigger sublimation in any object containing even modest amounts of water ice or other common volatiles. The implications of either possibility challenge established models of interstellar object composition and evolution, yet brightness measurements obtained through careful photometric monitoring tell an entirely different story that contradicts the visual evidence for inactivity. As the object approaches perihelion, its closest approach to the Sun during its hyperbolic passage through our solar system, it brightens by several magnitudes in ways that cannot possibly be explained by simple geometric effects related to changing distance and illumination angle. The physics of reflected sunlight from rotating bodies follows well-established mathematical relationships that account for distance-dependent flux variations and phase angle effects related to the geometry of Sun-object-Earth configurations. These calculations predict brightness changes that depend only on the object's intrinsic reflectivity, its cross-sectional area as seen from Earth, and its distance from both Sun and observer. The observed brightening of 3I/Atlas exceeds these theoretical predictions by factors that demand explanation through additional physical processes. The brightening pattern displays characteristics strongly reminiscent of classical cometary behavior, despite the complete absence of any accompanying visual evidence for outgassing activity that should produce detectable coma development. The magnitude increase follows curves similar to those displayed by well-studied comets, as volatile sublimation rates increase exponentially with decreasing heliocentric distance. Yet 3I/Atlas manages to brighten without developing any of the extended structures that such activity should inevitably produce. Some researchers propose that 3I/Atlas might be surrounded by an extraordinarily tenuous cloud of material too sparse to detect directly through conventional imaging techniques, but sufficient to scatter additional sunlight toward Earth-based observers through processes that enhance the object's apparent brightness. Such a scenario would require outgassing rates, orders of magnitude lower than those typical of known comets, producing material distributions so diffuse that they escape detection even by space-based telescopes operating under ideal observing conditions. Alternative hypotheses suggest that the object's surface might contain highly reflective regions or unusual mineral compositions that become more prominent as changing illumination angles reveal previously hidden features during its rotation. Perhaps the brightening results from exposure of subsurface materials with dramatically different optical properties, uncovered by thermal cycling or micrometeorite bombardment during the object's approach to perihelion. Spectroscopic monitoring conducted throughout this enigmatic brightening phase reveals subtle but potentially significant changes in the object's reflected light that hint at evolving surface conditions occurring over timescales of weeks to months. While the overall spectrum remains frustratingly featureless across all accessible wavelengths, careful analysis using the most sophisticated data reduction techniques detects slight variations in reflectivity at specific wavelengths that could indicate the presence of sublimating materials or gradually changing surface compositions. These spectral variations prove tantalizingly subtle, existing at the very limits of instrumental precision and requiring extensive statistical analysis to distinguish genuine signals from observational noise. the changes remain too ambiguous for definitive interpretation, creating what one frustrated researcher describes as tantalizingly inconclusive evidence for processes we cannot quite identify or confidently rule out. Yet, the mystery deepens considerably as increasingly precise astrometric observations reveal compelling evidence for material loss from the object's surface despite the persistent absence of any visible coma or extended structures. Careful tracking of 3 I/Atlas's trajectory, using positional measurements accurate to fractions of arc or seconds, detects tiny but statistically significant deviations from the purely gravitational motion predicted by solar system dynamics models. These non-gravitational accelerations suggest the gentle but persistent push imparted by escaping gas or dust particles as they leave the object's surface and carry away momentum in the process. The effect proves far subtler than the dramatic trajectory changes displayed by active comets during their most vigorous outgassing phases. Yet it remains clearly detectable through the accumulated precision of months of positional measurements obtained from observatories distributed across multiple continents. The magnitude of the implied mass loss rates presents a profound challenge to conventional understanding of how small bodies should behave when exposed to solar heating in the inner regions of planetary systems. If 3 I/Atlas is indeed losing material at rates sufficient to produce measurable trajectory modifications, fundamental questions arise about where that escaping material actually goes and why it fails to create the visible signatures that mark all other known outgassing objects. Current models of cometary physics predict that any significant mass loss should inevitably produce detectable coma development as escaping gases expand away from the nucleus and carry entrained dust particles into the surrounding space. The complete absence of such structures around 3 I/Atlas implies either that conventional models fail to describe the object's behavior or that it operates according to physical principles not yet incorporated into theoretical frameworks developed through study of solar system objects. Some researchers propose that 3 I/Atlas represents a fundamentally transitional object, perhaps an ancient comet that has exhausted most of its original volatile inventory during previous close approaches to other stars encountered during its interstellar journey, leaving behind a predominantly rocky body containing only trace amounts of sublimatable material insufficient to produce visible outgassing signatures. Such an evolutionary scenario could explain both the absence of obvious cometary activity and the subtle non-gravitational effects that suggest minimal ongoing mass loss. Others suggest that the object might be composed of exotic materials with highly unusual sublimation properties, unlike anything found among solar system objects. Substances that release gas and dust through mechanisms that differ fundamentally from the water-dominated chemistry typical of familiar comets. Perhaps 3 I/Atlas formed around a star with dramatically different chemical abundances, creating mineral assemblages or ice compositions that behave in ways that violate expectations based purely on solar system experience. The possibility that this interstellar visitor originated in a planetary system with radically different formation conditions adds layers of complexity to any attempt at theoretical interpretation. Stars spanning a wide range of masses and metallicities create environments where planetary formation occurs under chemical conditions that can differ dramatically from those that characterized our own solar nebula 4.5 billion years ago. Objects formed in such exotic environments might contain mineral assemblages, crystalline structures, or volatile inventories genuinely unknown within our local cosmic neighborhood, leading to thermal and outgassing behaviors that confound models developed exclusively through study of objects that condensed from the same primordial material cloud that gave birth to Earth and its planetary siblings. The mathematics of celestial mechanics operate with the cold precision of physical law, governing the motion of objects through space according to equations that Newton first formulated and Einstein later refined. Every asteroid, comet, and planetary body follows trajectories that can be calculated with extraordinary accuracy using these fundamental principles. Their paths through the solar system determined entirely by the gravitational influences of the Sun and planets. Yet 3I/Atlas moves through space in ways that subtly violate these mathematical certainties, displaying accelerations that cannot be explained by gravity alone. The discovery of this anomalous motion emerges through the patient accumulation of positional measurements obtained over months of careful observation. Astrometric observations, the precise determination of celestial coordinates, represent one of astronomy's most demanding technical challenges, requiring corrections for atmospheric refraction. Instrumental effects, stellar aberration, and dozens of other systematic influences that can introduce errors measured in tiny fractions of angular degrees. Professional observatories around the world contribute to this effort, each measurement adding precision to the growing data set that tracks 3I/Atlas's position against the background stars. The European Space Agency's Gaia spacecraft provides an extraordinarily accurate reference frame based on parallax measurements of more than 1 billion stars, creating a coordinate system stable enough to detect motions as small as micro-arc seconds over extended time periods. Initial orbital calculations, based on the first few weeks of observations, predict a trajectory that should carry 3I/Atlas along a mathematically perfect hyperbola determined solely by the Sun's gravitational field and the object's initial velocity upon entering the solar system. The predicted path curves elegantly around our star with the geometric precision that characterizes all gravitational interactions, following the same fundamental principles that govern planetary motion and spacecraft navigation. But as additional observations accumulate over subsequent months, subtle discrepancies begin to emerge between the predicted positions and the actual locations where telescopes find the object. These differences start as tiny deviations measured in fractions of arc seconds, angular distances so small that they would be invisible to any but the most precise astronomical instruments. Yet the deviations grow systematically over time, displaying patterns that suggest real physical effects rather than random observational errors. The magnitude of these positional anomalies proves remarkably small by everyday standards, yet their statistical significance becomes undeniable as the observational baseline extends across multiple months of tracking. The object consistently appears slightly ahead of its predicted position along its orbital path, as if some invisible force provides a gentle but persistent push that accelerates its motion in ways that pure gravitational dynamics cannot explain. Orbital dynamicists, scientists who specialize in the mathematical analysis of celestial motion, examine every possible source of systematic error that might produce such apparent acceleration without invoking non-gravitational forces. They consider atmospheric refraction effects that might bias ground-based observations, relativistic corrections that become important for objects moving at high velocities, and even the gravitational influences of asteroids and small moons whose masses might have been underestimated in standard solar system models. Each potential explanation proves insufficient to account for the observed deviations. The acceleration pattern displays characteristics that point unmistakably toward forces originating from the object itself rather than external gravitational influences or observational systematics. The direction of the anomalous acceleration aligns roughly with the object's motion around the Sun, suggesting a rocket-like effect produced by material escaping preferentially from specific regions of its surface. Similar non-gravitational accelerations have been observed in numerous comets, where they result from the asymmetric outgassing of volatile materials heated by solar radiation. As frozen gases sublimate from a comet's nucleus, they expand into space and carry away momentum through the familiar action-reaction principle that governs all rocket propulsion. The escaping material creates a gentle but measurable thrust that modifies the object's trajectory in predictable ways. The puzzling aspect of 3I/Atlas's behaviors lies not in the existence of non-gravitational acceleration. Such effects are well understood and routinely observed in active comets, but rather in the complete absence of any visible evidence for the outgassing processes that should produce such accelerations. Every known object that exhibits non-gravitational motion also displays obvious coma development, tail formation, or other clear signatures of active volatile sublimation. Theoretical calculations suggest that producing the observed acceleration requires mass loss rates on the order of several kilograms per second, modest by cometry standards, but substantial enough that conventional models predict obvious coma development should accompany such activity. The fact that 3I/Atlas manages to lose material at rates sufficient to modify its trajectory while remaining visually indistinguishable from an inert asteroid challenges fundamental understanding of outgassing physics. Some researchers propose that the object might be losing material through mechanisms that differ qualitatively from typical cometary outgassing. Perhaps the escaping material consists of individual molecules or atomic species that remain invisible to optical observation but still carry sufficient momentum to produce measurable trajectory changes. Such a scenario would require surface processes that selectively release gas without entraining the dust particles that create visible coma structures. Alternative hypotheses suggest that 3I/Atlas might be experiencing thermal effects related to its rotation and surface properties rather than conventional outgassing. The Yarkovsky effect, a subtle force that results from thermal radiation pressure as rotating objects absorb sunlight and re-emit it as infrared radiation, can produce small but measurable accelerations over extended time periods. However, calculations indicate that this mechanism alone cannot account for the magnitude of the observed trajectory modifications. The mystery deepens when researchers attempt to model the object's interior structure and composition based on the observed acceleration patterns. Different outgassing scenarios predict different relationships between the non-gravitational acceleration and the object's distance from the Sun, its rotation state, and its thermal properties. The actual behavior of 3I/Atlas fits none of these theoretical frameworks precisely, suggesting either that current models remain incomplete or that the object operates according to physical principles not yet incorporated into standard theory. Advanced computer simulations attempt to reproduce the observed trajectory modifications through various combinations of composition, internal structure, and thermal evolution. Models that successfully predict the magnitude of non-gravitational acceleration often fail to explain the absence of visible outgassing signatures. Conversely, scenarios that account for the lack of obvious coma development typically predict trajectory changes too small to match observations. The accumulating evidence suggests that 3I/Atlas exists in a regime of behavior that lies between the well-understood extremes of completely inert asteroids and vigorously outgassing comets. The object appears to be losing material at rates that fall into a narrow range where non-gravitational effects remain detectable through precise astrometry, while the escaping material remains below the threshold for visual detection even by space-based telescopes. This intermediate behavior regime may be more common among interstellar objects than among solar system natives, reflecting the different evolutionary histories and compositional characteristics of matter formed in other planetary systems. Objects that have spent millions of years in the cold vacuum between stars may have developed surface properties or internal structures that lead to outgassing behaviors unlike anything observed among objects that formed within our own solar neighborhood. Professional astronomers find themselves confronting an object that challenges not only specific theoretical models, but also the broader assumption that sufficient observational data will inevitably lead to clear understanding. 3I/Atlas continues to accelerate through space according to forces that remain essentially mysterious despite months of intensive study using the world's most sophisticated astronomical instruments. The trajectory anomaly represents more than a simple observational puzzle. It embodies the humbling recognition that the universe contains physical processes that persist in defying human attempts at complete understanding. Regardless of how precise our measurements become, or how comprehensive our theoretical frameworks appear to be, the spectroscopic analysis of celestial objects represents one of astronomy's most powerful investigative techniques, a method that allows scientists to decode the chemical composition of distant worlds by examining the subtle fingerprints that atoms and molecules imprint upon reflected or emitted light. When starlight bounces off an asteroid's surface or passes through a comet's expanding coma, it carries with it a wealth of information about the materials it has encountered, creating absorption features at specific wavelengths that correspond to known atomic and molecular transitions with the reliability of cosmic barcodes. This technique has proven so successful that astronomers routinely determine the composition of objects billions of kilometers away with greater precision than early chemists achieved for terrestrial samples held directly in their hands. Iron-rich asteroids reveal themselves through characteristic absorption bands produced by olivine and pyroxene minerals. Ice-dominated comets display the unmistakable signatures of water vapor. Carbon dioxide, methane, and complex organic compounds as these materials sublimate under solar heating and interact with incoming photons. The spectroscopic investigation of 3I/Atlas begins with the same confident expectations that have guided countless previous studies of small solar system bodies. Researchers anticipate that careful analysis of the object's reflected sunlight will reveal diagnostic features that clearly indicate its surface composition, formation environment, and evolutionary history. The accumulated experience of decades suggests that virtually every solid object in space displays spectral characteristics that allow classification within well-established taxonomic schemes. Yet from the very first observations, 3I/Atlas presents a spectrum that defies these reasonable expectations with the stubborn persistence of an object determined to conceal its secrets. The reflected light appears remarkably uniform across all accessible wavelengths, displaying an almost perfectly flat reflectance that varies little from the ultraviolet through the near-infrared regions where most diagnostic mineral features should appear prominently. This spectral neutrality proves deeply frustrating to researchers accustomed to reading cosmic chemistry through the subtle language of absorbed and reflected photons. The object's spectrum resembles a featureless continuum more characteristic of laboratory measurements of artificial materials specifically designed to have uniform optical properties than the complex absorption patterns typical of natural planetary surfaces shaped by billions of years of geological and space weathering processes. Professional spectrographs attached to major telescopes around the world contribute observations across different wavelength ranges, each instrument adding precision and spectral coverage to the growing dataset. The high resolution. A Shell spectrometer at the Keck Observatory provides unprecedented detail in the near-infrared, where many silicate minerals display their most prominent absorption features. The Space Telescope Imaging Spectrograph aboard Hubble extends coverage into the ultraviolet, where atomic species often reveal their presence through electronic transitions. Each new observation confirms the same puzzling result. 3I/Atlas appears almost perfectly gray across the electromagnetic spectrum, reflecting sunlight with uniform efficiency that suggests either a highly unusual surface composition unlike anything commonly found among solar system objects, or perhaps a covering of material that has been processed by cosmic radiation and micrometeorite bombardment during its interstellar journey to the point where all diagnostic spectral features have been effectively erased. The implications of this spectral flatness extend far beyond simple compositional uncertainty. Most theoretical models of planetary formation predict that objects should display spectral characteristics that reflect their formation environment and subsequent evolutionary history. Rocky bodies formed in the inner regions of planetary systems should show evidence of high-temperature mineral assemblages. Icy objects from outer system regions should retain spectral signatures of volatile compounds that condense only at very low temperatures. Interstellar objects should carry the chemical fingerprints of their stellar birthplaces. potentially revealing exotic compositions that reflect the different nucleosynthetic processes occurring in stars with masses and metallicities dramatically different from our Sun. The complete absence of such diagnostic features in 3I/Atlas's spectrum suggests either that conventional spectroscopic interpretation techniques fail when applied to truly foreign materials, or that the object has undergone surface modification processes that obscure its original composition. Space weathering effects, the gradual alteration of surface materials through bombardment by cosmic rays, solar wind particles, and micrometeorites, might account for some degree of spectral modification over the extended timescales characteristic of interstellar travel. Laboratory experiments demonstrate that such processes can indeed alter the optical properties of common minerals, generally causing spectral features to become less prominent and overall reflectance to decrease as surface materials develop thin coatings of metallic iron and other space-weathering products. However, the degree of spectral neutrality displayed by 3I/Atlas exceeds what current space-weathering models predict should occur even after millions of years of exposure to the harsh interstellar environment. The object's spectrum appears more severely altered than surfaces of the most ancient asteroids in our own solar system, despite the fact that these objects have experienced continuous bombardment for over 4 billion years, while remaining within the relatively protective environment of the heliosphere. Advanced laboratory studies attempt to reproduce the observed spectral characteristics through various combinations of composition and processing. Researchers subject meteorite samples and synthetic mineral mixtures to bombardment by energetic particles, extreme temperature cycling, and other conditions designed to simulate the interstellar environment. While such experiments succeed in modifying spectral properties to some degree, none reproduce the extreme neutrality characteristic of 3I/Atlas across such a broad wavelength range. The possibility that this interstellar visitor contains materials genuinely unknown within our solar system adds another layer of complexity to spectroscopic interpretation. Different stellar environments produce planetary systems with chemical abundances that can differ dramatically from solar composition, potentially creating mineral assemblages or crystalline structures that lack terrestrial analogues. Such exotic materials might display optical properties that fall outside the range of laboratory reference spectra developed through study of meteorites and terrestrial samples. Theoretical calculations suggest that certain hypothetical mineral compositions could indeed produce the nearly featureless spectra observed in 3I/Atlas. But these calculations require invoking materials with unusual properties that have never been directly observed or synthesized under laboratory conditions. The theoretical minerals would need to combine high reflectance with complete absence of characteristic absorption features across multiple octaves of electromagnetic spectrum, a combination of properties that challenges current understanding of how atoms and molecules interact with photons. Some researchers propose that 3I/Atlas might be covered by a layer of organic compounds produced through cosmic ray processing of simple carbon-bearing molecules during its interstellar journey. Certain classes of complex organic polymers display relatively featureless spectra that could potentially account for the observed optical properties. However, such materials typically exhibit much lower reflectance than observed, and they should display at least some weak absorption features in the near-infrared, where CH and other molecular bonds create detectable signatures. The mystery deepens when researchers examine the subtle temporal variations in 3I/Atlas's spectrum as it rotates and approaches closer to the Sun. While the overall spectrum remains frustratingly neutral, sophisticated data analysis techniques detect extremely weak variations in reflectance at specific wavelengths that might indicate gradual changes in surface composition or the exposure of subsurface materials with slightly different optical properties. These spectral variations exist at the very limits of instrumental precision, requiring extensive statistical analysis to distinguish genuine signals from observational noise and systematic effects. The changes prove too subtle for definitive interpretation, existing in the ambiguous realm where potential discoveries await confirmation through additional observations or improved measurement techniques. Some features appear to strengthen slightly as the object approaches perihelion, suggesting possible thermal effects or the gradual exposure of materials previously hidden beneath surface layers. The accumulated spectroscopic evidence presents astronomers with a profound puzzle that extends beyond the specific case of 3Y/Atlas to challenge fundamental assumptions about how matter behaves in interstellar environments. The complete absence of diagnostic spectral features suggests either that current understanding of space weathering processes remains incomplete, or that this object represents a completely new class of interstellar body with properties unlike anything previously observed. Professional astronomers find themselves confronting the uncomfortable possibility that some cosmic objects may be inherently resistant to spectroscopic analysis. That the very techniques which have proven so successful for studying solar system objects may fail when applied to matter that has undergone the extreme processing associated with millions of years of interstellar travel through environments far more hostile than anything experienced within the protective bubble of our heliosphere. The universe, it appears, has provided Earth scientists with an object specifically designed to demonstrate the limitations of even the most sophisticated analytical techniques, reminding them that the cosmos contains materials and processes that may forever remain partially opaque to human investigation. Regardless of how advanced our instruments become or how comprehensive our theoretical models appear, the fundamental challenge of determining an object's physical characteristics from astronomical observations becomes particularly acute when dealing with 3I/Atlas, whose size estimates fluctuate wildly depending upon which observational technique researchers employ and which theoretical assumptions they invoke to interpret their measurements. The object presents astronomers with a cosmic riddle wrapped in the deceptive simplicity of reflected photons, where each new approach to size determination yields results that contradict previous estimates while adding layers of complexity to an already perplexing mystery. Traditional asteroid size determination relies upon the well-established relationship between an object's brightness, its distance from both Sun and Earth, and its surface reflectivity or albedo. This straightforward approach has proven reliable for thousands of solar system objects, allowing astronomers to calculate diameters with reasonable precision even for bodies too small and distant for direct imaging. The technique assumes that observed brightness results primarily from reflected sunlight, with contributions proportional to the object's cross-sectional area and surface reflectivity. Initial size estimates for 3I/Atlas, based upon its apparent magnitude and assuming typical asteroid albedo values, suggest an object several hundred meters in diameter, large enough to be significant but not unusually so by solar system standards. Such dimensions would place it among the more substantial interstellar visitors, larger than Oumuamua, but smaller than many short-period comets that regularly grace the inner solar system with predictable appearances. However, these preliminary calculations assume surface reflectivity values derived from studies of solar system asteroids, an assumption that may prove entirely inappropriate for an object that has spent millions of years traveling through the hostile interstellar environment. Space weathering processes operating over such extended timescales could alter surface optical properties in ways that render standard albedo assumptions meaningless, leading to size estimates that could be wrong by factors of several or more. Thermal observations obtained using infrared-sensitive instruments provide an alternative approach to size determination that should prove independent of surface reflectivity assumptions. The technique measures the amount of thermal radiation emitted by solar heating, which depends upon the object's total surface area and thermal properties rather than its albedo. Combined with visible light brightness measurements, thermal observations allow astronomers to solve simultaneously for both size and reflectivity using well-established radiometric techniques, The thermal observations of 3I/Atlas yield results that contradict the size estimates derived from visible light measurements in ways that suggest either that the standard radiometric models fail for this object, or that its thermal properties differ dramatically from those of typical solar system bodies. The thermal emission appears too strong for an object of the size suggested by optical observations, implying either a much larger cross-sectional area or surface materials with unusual thermal emissivity characteristics. These contradictory results force researchers to consider the possibility that 3I/Atlas possesses an extremely unusual shape that dramatically affects both its optical and thermal signatures. Perhaps the object is highly elongated, resembling a cosmic needle or rod that presents dramatically different cross-sectional areas depending upon viewing geometry. Such extreme shapes are rare among solar system objects, but not unknown, with Oumuamua providing a precedent for interstellar bodies, with aspect ratios far exceeding those typical of asteroids or comet nuclei. Advanced computer modeling attempts to reconcile the optical and thermal observations through various combinations of shape, size, and surface properties. The models that successfully reproduce both sets of measurements require invoking object characteristics that stretch the boundaries of physical plausibility, suggesting either extreme elongation ratios exceeding 10:1 or surface compositions with thermal properties unlike anything observed among solar system objects. The rotation of 3I/Atlas adds another layer of complexity to size determination efforts, as the object's brightness varies significantly over its rotational period in ways that should provide direct information about its shape and dimensions. However, the observed light curve displays characteristics that fit poorly with simple geometric models of rotating ellipsoids, suggesting either that the object possesses an extremely irregular shape or that its surface contains regions with dramatically different reflectivity properties. Photometric analysis reveals brightness variations that exceed what conventional asteroid models predict for objects with reasonable axis ratios, implying either extreme elongation or surface features that create brightness changes through mechanisms other than simple geometric effects. Some researchers propose that 3I/Atlas might possess a highly irregular surface topography, with ridges, valleys, or crater-like features that create shadowing effects as the object rotates under different illumination conditions. The possibility that 3I/Atlas consists of multiple components, perhaps a contact binary or a loose aggregate of smaller bodies held together by weak gravitational forces, offers another potential explanation for its unusual size and brightness characteristics. Such composite structures are common among solar system asteroids and could account for both the irregular light curve and the difficulty in reconciling optical and thermal observations through single-body models. Radar observations attempted by several major planetary radar facilities failed to detect any return signal from 3I/Atlas, despite the object's relatively close approach to Earth during portions of its trajectory. This absence of radar detection could result from the object's small size, unusual shape, or surface properties that scatter radio waves in ways that prevent coherent returns from reaching terrestrial receivers. However, the radar non-detection also establishes upper limits on the object's size and radar cross-section that must be incorporated into comprehensive models of its physical characteristics. High-resolution imaging attempts using the largest ground-based telescopes and space-based observatories consistently show 3I/Atlas as a point source indistinguishable from background stars, providing no direct information about its shape or surface features. Even the Hubble Space Telescope, with its exceptional optical resolution, cannot resolve the object into a measurable disk, indicating that its angular size remains smaller than a few milliarc seconds as seen from Earth. The accumulated observational evidence suggests that 3I/Atlas possesses physical characteristics that exist at the boundaries of what current astronomical techniques can reliably measure and interpret. The object appears simultaneously too small for direct imaging, yet large enough to produce significant thermal emission, too regular for extreme elongation, yet too variable for simple spherical geometry, too bright for low albedo, yet too thermally active for high reflectivity. These contradictory characteristics point toward fundamental limitations in the techniques astronomers use to study small, distant objects, particularly those with properties that fall outside the range of solar system experience. The methods that have proven reliable for asteroids and comets may simply prove inadequate for objects that formed under different conditions and have experienced evolutionary histories unlike anything represented in our local cosmic neighborhood. Professional astronomers find themselves confronting an object that embodies the practical limitations of remote sensing techniques, demonstrating how even the most sophisticated observational methods can yield ambiguous or contradictory results when applied to phenomena that challenge the assumptions underlying their theoretical foundations. 3I/Atlas continues its journey through our solar system, carrying with it secrets about its physical nature that may remain permanently beyond the reach of Earth-based investigation. The mystery of material loss from 3Y/Atlas deepens with each attempt to understand the mechanisms by which this enigmatic object sheds mass while remaining visually indistinguishable from an inert asteroid. Evidence for ongoing outgassing emerges not from direct observation of escaping material, but through the subtle testimony of altered trajectories and unexplained brightness variations that hint at processes occurring beneath the threshold of conventional detection methods. Traditional cometary outgassing follows well-understood physical principles that have been validated through decades of spacecraft encounters and telescopic observations. As frozen volatiles in a comet's nucleus absorb solar energy, they undergo phase transitions from solid directly to gas through the process of sublimation, creating expanding clouds of vapor that drag entrained dust particles away from the surface and into the surrounding space. This escaping material creates the characteristic coma and tail structures that make active comets visible across vast distances. The rate of mass loss depends upon several factors, including the amount of volatile material present, the intensity of solar heating, and the efficiency with which sublimated gases can escape from the object's interior to its surface. Computer models predict that objects containing even modest amounts of water ice should begin outgassing at heliocentric distances of several astronomical units, creating detectable coma development long before reaching perihelion. 3I/Atlas violates these predictions in ways that challenge fundamental understanding of how volatile-rich objects should behave in the inner solar system. The object displays clear evidence of non-gravitational acceleration that implies ongoing mass loss at rates of several kilograms per second. Yet it maintains the sharp, point-like appearance of a completely inactive body throughout its passage from the outer solar system to perihelion and beyond. Thermal models suggest that any object containing significant amounts of water ice should develop obvious outgassing signatures when heated by solar radiation to temperatures exceeding the sublimation threshold of approximately 200 Kelvin. As 3I/Atlas approaches to within 2 astronomical units of the Sun, its surface temperature should rise well above this critical value, triggering vigorous sublimation of any exposed ice and creating easily detectable coma development. The complete absence of visible outgassing signatures, despite clear evidence for mass loss, forces researchers to consider mechanisms that could produce material ejection without creating the extended structures typical of conventional cometary activity. Perhaps the escaping material consists primarily of individual gas molecules that remain invisible to optical observation while still carrying sufficient momentum to alter the object's trajectory through rocket-like effects. Such a scenario would require surface processes that selectively release volatile gases without entraining the dust particles that create visible coma structures around active comets. Laboratory experiments demonstrate that sublimation, under very low pressure conditions can indeed favor gas escape over dust entrainment, but the extreme efficiency required to explain 3I/Atlas's behavior exceeds what these studies suggest should occur under realistic surface conditions. Alternative hypotheses propose that the object might be losing material through mechanisms entirely different from conventional sublimation processes. Perhaps thermal cycling as 3I/Atlas rotates in and out of direct sunlight creates mechanical stresses that fracture surface materials and eject small particles at velocities too low to escape completely, but sufficient to alter the object's momentum slightly. Such a process might occur without producing detectable coma development if the ejected particles remain gravitationally bound and eventually fall back to the surface. The possibility that 3I/Atlas possesses an extremely porous or low-density internal structure adds another dimension to the outgassing puzzle. Highly porous objects might allow volatile gases to escape through complex networks of internal voids and fractures, potentially creating distributed outgassing over large surface areas rather than the localized jets typical of denser cometary nuclei. Such distributed activity might remain below the detection threshold for individual outgassing regions while still producing measurable net mass loss. Spectroscopic monitoring throughout the object's solar approach reveals tantalizing hints of temporal variations that might indicate evolving outgassing activity occurring at levels too subtle for direct detection. While the overall spectrum remains frustratingly featureless, careful analysis detects extremely weak variations in reflectance at specific wavelengths that could result from changing surface compositions as volatile materials sublimate and expose underlying layers with different optical properties. These spectral changes prove too subtle for definitive interpretation. Existing at the boundary between genuine physical effects and instrumental noise, some variations appear to correlate with the object's rotational period, suggesting that outgassing might indeed be occurring from localized surface regions that become exposed to direct sunlight as 3I/Atlas tumbles through space. Other spectral features seem to strengthen gradually as the object approaches perihelion, potentially indicating increased outgassing rates in response to intensifying solar heating. The search for outgassing signatures extends beyond optical wavelengths to include radio observations that might detect molecular emissions from escaping gases, water vapor, carbon monoxide, and other common cometary volatiles emit characteristic radiospectral lines when excited by solar radiation or collisional processes in expanding comas. Several major radio astronomy facilities conduct sensitive searches for such emissions from 3I/Atlas, attempting to detect outgassing activity through techniques that remain sensitive to gas production rates far below the threshold for optical coma detection. These radio observations yield uniformly negative results, establishing stringent upper limits on the production rates of common volatile species that fall well below the levels required to explain the object's non-gravitational acceleration through conventional outgassing mechanisms. The absence of detectable molecular emissions forces researchers to consider either that 3I/Atlas is losing material through processes that do not involve the release of radioactive molecules, or that the escaping material consists of species that remain undetectable at radio wavelengths. Advanced computer simulations attempt to model the outgassing behavior of objects with compositions and internal structures that might account for the observed characteristics of 3I/Atlas. These models explore scenarios involving exotic volatile species with unusual sublimation properties, complex internal structures that modify outgassing dynamics, and surface materials that suppress dust entrainment while allowing gas escape. The simulations that most successfully reproduce the observed combination of mass loss and coma absence require invoking object properties that stretch the boundaries of physical plausibility. The models suggest that 3I/Atlas might possess an internal structure so highly processed by its interstellar journey that conventional outgassing models simply do not apply, or that it contains volatile materials with properties unlike anything found among solar system objects. Professional astronomers find themselves confronting an object that challenges not only specific theoretical models of outgassing physics, but also the broader assumption that sufficient observational coverage will inevitably reveal the physical processes responsible for observed phenomena. 3I/Atlas continues to lose material through mechanisms that remain essentially invisible despite intensive monitoring using the world's most sophisticated astronomical instruments. The rotational behavior of 3I/Atlas emerges as yet another piece of a cosmic puzzle that refuses to yield to conventional interpretation, displaying characteristics that challenge fundamental assumptions about how solid objects should tumble through the vacuum of space when freed from planetary gravitational constraints. The object's rotation carries within its mathematical patterns clues about its internal structure, formation history, and evolutionary processes. Yet these clues prove as enigmatic as every other aspect of this interstellar visitor. Determining the rotation period of a distant asteroid or comet relies upon careful photometric monitoring that tracks brightness variations as the object tumbles through space. Most small solar system bodies rotate with periods ranging from a few hours to several days, spinning with the dignity of objects that have achieved rotational equilibrium under the influence of their own gravity and the various torques they have experienced throughout their lifetimes. The rotation of such objects typically results from the conservation of angular momentum inherited from the chaotic collision processes that shaped the early solar system. Impacts, gravitational encounters, and other dynamical interactions impart rotational energy that persists for billions of years in the absence of significant dissipative forces. The final spin states reflect a complex history of angular momentum exchange that generally produces rotation periods consistent with gravitational stability and structural integrity. Initial photometric observations of 3I/Atlas reveal brightness variations that repeat with a period of approximately 2.5 hours, suggesting rotation significantly faster than typical for objects of its estimated size. This rapid rotation alone proves somewhat unusual, as larger objects generally spin more slowly due to structural limitations that prevent very fast rotation without catastrophic breakup. The rotation rate implies either that 3I/Atlas is smaller than current size estimates suggest, or that it possesses unusually high structural strength that allows rapid spinning without disintegration. However, detailed analysis of the light curve reveals rotational behavior far more complex than simple single-axis spinning would produce. The brightness variations display characteristics that suggest either an extremely irregular shape with multiple rotational modes, or a compound system consisting of multiple components with different rotational properties. The photometric signature contains periodicities that cannot be explained through the rotation of a single, coherent body under standard gravitational dynamics. Advanced period analysis techniques reveal evidence for what appears to be a tumbling motion, where the object rotates simultaneously about multiple axes in ways that create complex brightness variations over extended time periods. Such non-principal axis rotation typically results from recent impacts or other disruptive events that impart angular momentum in directions that do not align with the object's principal moments of inertia. Tumbling motion gradually evolves toward principal axis rotation through internal energy dissipation, a process that typically requires thousands to millions of years depending upon the object's internal structure and composition. The observation of active tumbling in 3I/Atlas could indicate either that the object experienced a recent collision during its interstellar journey, or that its internal properties prevent the usual evolution towards stable rotation. The possibility that 3I/Atlas consists of multiple components held together by weak gravitational or cohesive forces adds another layer of complexity to its rotational dynamics. Contact binaries and rubble pile asteroids display rotational characteristics that differ significantly from those of monolithic objects, often exhibiting multiple periodicities that reflect the independent motion of constituent components as well as the overall system rotation. Such composite structures are common among solar system asteroids, where they result from gentle collisions that allow disrupted fragments to reaccumulate under their own gravity without completely destroying the original body. The weak gravitational fields typical of small objects cannot hold together material that rotates too rapidly, creating natural limits on rotation rates that depend upon the object's size and internal density distribution. Theoretical calculations suggest that 3I/Atlas's rapid rotation approaches or exceeds these stability limits for objects with typical asteroid densities, implying either that the object possesses unusually high internal strength or that it has a lower density than conventional estimates suggest. Both possibilities challenge current understanding of the object's composition and structural properties. The rotational evolution of objects during interstellar travel represents a largely unexplored aspect of small body dynamics. The extreme environment between stars subjects traveling objects to cosmic ray bombardment, thermal cycling, and micrometeorite impacts that could gradually alter rotational properties over millions of years. Such processes might create internal structures or surface modifications that lead to rotational behavior unlike anything observed among solar system objects. Sophisticated computer models attempt to reproduce the observed rotational characteristics through various combinations of shape, internal structure, and evolutionary history. The simulations that most successfully match the complex light curve of 3I/Atlas require invoking object properties that challenge conventional understanding of how small bodies maintain structural integrity while experiencing rapid rotation. Some models suggest that the object might possess an extremely elongated shape with unusual mass distribution that allows stable rotation despite apparent violations of conventional stability criteria. Others propose that 3I/Atlas might be experiencing ongoing structural evolution, perhaps slowly disintegrating under rotational stress in ways that create time-variable photometric signatures. The possibility that rotational behavior itself provides evidence for ongoing outgassing adds another dimension to the mystery. Asymmetric mass loss from rotating objects can create torques that alter rotational properties over relatively short timescales, potentially explaining some of the complex periodicities observed in 3I/Atlas's light curve. However, such effects typically require outgassing rates that should produce easily detectable coma development. Professional astronomers conducting the photometric monitoring program find their observations consistently challenging theoretical expectations about how objects should behave under the conditions that 3I/Atlas experiences. Each new night of data adds complexity to an already puzzling rotational signature that resists interpretation through conventional models of small body dynamics. The accumulated evidence suggests that 3I/Atlas rotates according to principles that extend beyond the range of solar system experience, possibly reflecting evolutionary processes or structural characteristics that develop only during the extreme conditions associated with interstellar travel. The universe has provided Earth scientists with an object whose very motion through space embodies mysteries that may require fundamentally new approaches to small body physics. The thermal behavior of 3I/Atlas presents astronomers with perhaps the most perplexing aspect of an already enigmatic object, displaying temperature characteristics that violate fundamental predictions about how solid bodies should respond to solar heating in the inner regions of planetary systems. The object's thermal properties emerge through infrared observations that measure the amount of heat radiated into space. Yet these measurements yield results that challenge basic understanding of thermodynamics and surface physics. Thermal emission from small solar system bodies follows well-established physical principles that relate surface temperature to distance from the sun, surface composition, thermal inertia, and rotation rate. These relationships have been validated through decades of observations and spacecraft encounters that demonstrate remarkable consistency between theoretical predictions and measured temperatures for objects ranging from near-Earth asteroids to distant comets approaching from the outer solar system. The fundamental physics involved are straightforward. Objects absorb solar energy at rates proportional to their cross-sectional area and the intensity of incident sunlight, while radiating energy back to space at rates determined by their surface temperature and emissivity. The equilibrium temperature results from balancing energy input against energy output, creating predictable relationships that allow astronomers to infer surface properties from thermal observations. Initial thermal measurements of 3I/Atlas, obtained using infrared-sensitive instruments at several major observatories, reveal surface temperatures that appear too warm for an object at its observed distance from the Sun. The measured thermal emission suggests temperatures exceeding what standard models predict by margins that cannot be explained through reasonable variations in surface composition or thermal properties. This temperature anomaly becomes more pronounced as detailed analysis reveals that the thermal emission varies in ways that do not correlate simply with the object's rotation or changing distance from the Sun. While most asteroids display thermal variations that reflect their spin state and the diurnal temperature cycle that results from rotating in and out of direct sunlight, 3I/Atlas exhibits thermal behavior that appears almost independent of these geometric factors. Advanced thermal models attempt to explain the observed characteristics through various combinations of surface properties, internal heat sources, and unusual geometric configurations. The models that successfully reproduce the measured temperatures require invoking thermal properties unlike anything observed among solar system objects, suggesting either exotic surface compositions or internal processes that generate additional heat beyond simple solar absorption. The possibility that 3I/Atlas possesses extremely low thermal inertia, a measure of how quickly surface materials respond to changing thermal conditions, could potentially account for some aspects of its unusual thermal behavior. Objects with very low thermal inertia heat and cool rapidly in response to changing solar illumination, creating thermal signatures that differ significantly from those of more thermally massive bodies. However, the degree of thermal responsiveness required to explain the observations exceeds what laboratory measurements suggest should occur even for the most thermally sensitive materials known to science. The implied thermal properties would require surface materials with heat capacities and thermal conductivities that fall outside the range of any naturally occurring substances that have been studied under controlled conditions. Alternative explanations invoke the possibility that 3I/Atlas contains internal heat sources that supplement solar heating and create thermal emission patterns that appear anomalous when interpreted through conventional models. Such internal heating could result from radioactive decay of unstable isotopes, mechanical friction associated with structural instability, or exotic chemical processes that occur within the object's interior. Radioactive heating provides a plausible mechanism for internal energy generation, particularly if 3I/Atlas formed in an environment enriched in heavy elements that create long-lived isotopes capable of generating significant thermal energy over extended timescales. Different stellar environments produce planetary systems with dramatically different abundances of radioactive elements, potentially creating objects with internal heat generation capabilities far exceeding those typical of solar system bodies. However, calculations suggest that producing the observed thermal anomalies through radioactive decay alone would require isotope concentrations that exceed reasonable estimates based on nucleosynthetic processes occurring even in the most extreme stellar environments. The required heat generation rates approach levels that would destabilize the object's structure through thermal expansion and outgassing over timescales much shorter than its presumed age. The possibility that mechanical processes generate internal heating offers another potential explanation for the thermal anomalies. If 3I/Atlas possesses a complex internal structure with components that move relative to each other, perhaps a loosely bound rubble pile or a contact binary system, then tidal forces and rotational dynamics could create frictional heating that supplements solar energy input. Such mechanical heating mechanisms have been observed in some solar system objects, particularly those experiencing strong tidal forces from nearby massive bodies or those with complex internal structures that allow relative motion between constituent components. However, the isolated environment that 3I/Atlas experiences during its passage through our solar system provides no obvious source of external tidal forces that could drive significant mechanical heating. Thermal observations obtained at different wavelengths reveal spectral characteristics of the emitted radiation that provide additional constraints on surface composition and temperature distribution. The thermal spectrum of 3I/Atlas displays features that suggest either unusual emissivity properties or temperature gradients across the object's surface that differ from those predicted by standard thermal models. Some measurements indicate thermal emission that appears too intense at certain infrared wavelengths, suggesting either surface materials with unusually high emissivity at those specific wavelengths, or temperature distributions that concentrate thermal energy in ways that conventional models fail to predict. Other spectral features hint at temporal variations in thermal properties that could indicate evolving surface conditions or internal processes that change over timescales of days to weeks. The accumulated thermal observations present researchers with an object that appears to violate fundamental assumptions about how matter responds to solar heating in the vacuum of space. Professional astronomers find their most sophisticated thermal models consistently failing to reproduce the observed characteristics without invoking properties that challenge basic understanding of thermodynamics and materials science. The thermal behavior of 3I/Atlas embodies the broader mystery of an object that seems designed to confound every attempt at scientific explanation, displaying properties that individually might be accommodated within existing theoretical frameworks but collectively resist integration into any coherent physical model. The universe has provided Earth scientists with a thermal puzzle that may require fundamentally new approaches to understanding how matter behaves under the extreme conditions associated with interstellar travel and formation in exotic environments. The quest to determine the cosmic origins of 3I/Atlas leads astronomers into the vast archives of stellar motion and galactic dynamics, where they attempt to trace the object's trajectory backward through space and time to identify the stellar system from which this enigmatic visitor originally departed. This investigation represents one of the most challenging exercises in celestial detective work, requiring precise knowledge of the object's current velocity vector combined with sophisticated models of how stars move through the galaxy over millions of years. The fundamental approach to determining interstellar object origins relies upon integrating the object's motion backward through time while accounting for the gravitational influences of all significant masses that could have affected its trajectory during its journey between stars. This calculation must consider not only the motion of our own solar system through the galaxy, but also the complex orbital dynamics of hundreds of nearby stars whose gravitational fields could have deflected the object from its original path. Initial attempts to identify the source of 3I/Atlas begin with precise measurements of its current velocity relative to the local standard of rest, the average motion of stars in our galactic neighborhood. These measurements reveal a velocity vector that carries the object through our solar system at approximately 44 kilometers per second relative to the Sun, with a trajectory that suggests arrival from the direction of the constellation Lynx. However, the precision required for reliable source identification exceeds what current observational techniques can achieve with complete confidence. Small uncertainties in velocity measurements propagate exponentially over the vast distances and long timescales involved in interstellar travel, creating error ellipses that expand to encompass large volumes of space after integrating backward over millions of years. Advanced computer simulations attempt to constrain possible origins by modeling the gravitational environment that 3I/Atlas has traversed during its interstellar journey. These calculations must account for the changing positions of potentially hundreds of nearby stars, each following its own complex orbit around the galactic center while participating in the collective motion of stellar associations and moving groups. The Gaia spacecraft's unprecedented astrometric catalog provides the foundation for these investigations, offering precise measurements of stellar positions, proper motions, and parallax distances for more than 1 billion stars in our galactic neighborhood. This database allows astronomers to reconstruct the three-dimensional motions of nearby stellar systems with sufficient accuracy to trace their positions backward over timescales relevant to interstellar object travel. Initial analyses identify several candidate stellar systems that could potentially represent the origin point of 3I/Atlas based on geometric considerations alone. These candidates include relatively nearby stars whose past positions along 3I/Atlas's back-projected trajectory suggest possible gravitational encounters that could have ejected the object from their planetary systems millions of years ago. However, each potential source system presents significant problems when subjected to detailed scrutiny. The timing of proposed ejection events often requires stellar encounters that occurred when the candidate stars occupied positions incompatible with their known orbital dynamics. Other scenarios demand gravitational interactions of precisely the right strength and geometry to accelerate 3I/Atlas to its observed velocity while sending it on a trajectory that would eventually bring it to our solar system. The possibility that 3I/Atlas originated from a stellar system that has since been disrupted or significantly altered adds another layer of complexity to origin determination efforts. Young stellar associations and open star clusters gradually disperse over timescales of tens to hundreds of millions of years as gravitational interactions and galactic tidal forces scatter their constituent stars throughout the galaxy. If 3I/Atlas was ejected from a star that belonged to such a dispersed association, then its original source might no longer exist as a coherent system that can be identified through current stellar catalogs. The object could represent a fossil remnant of planetary formation processes that occurred in stellar environments that have since evolved beyond recognition or disappeared entirely through stellar evolution processes. Alternative scenarios propose that 3I/Atlas might have originated from much more distant stellar systems, traveling for hundreds of millions or even billions of years before reaching our solar system. Such extended journeys would make source identification essentially impossible using current techniques, as the gravitational perturbations and measurement uncertainties accumulated over such vast timescales render backward trajectory integration meaningless. The chemical composition of 3Y/Atlas, if it could be determined with sufficient precision, might provide independent constraints on its origin by revealing isotopic signatures characteristic of specific stellar nucleosynthetic environments. Different types of stars produce planetary systems with dramatically different chemical abundances, potentially creating objects whose compositions carry the fingerprints of their formation environments encoded in isotope ratios and trace element concentrations. However, the frustratingly featureless spectrum of 3E/Atlas prevents such compositional analysis, denying astronomers access to what could be the most definitive evidence for the object's stellar birthplace. The absence of diagnostic spectral features leaves researchers dependent entirely upon dynamical arguments that prove insufficient for reliable source identification given current observational precision. Some investigators propose that 3I/Atlas might not have originated from any specific stellar system, but instead represents a truly primordial object that condensed directly from the interstellar medium during the galaxy's early history. Such objects could exist as fossil remnants of galactic chemical evolution processes that occurred billions of years ago when the Milky Way possessed dramatically different structure and composition. This speculative possibility would make 3I/Atlas an artifact of cosmic archaeology, carrying within its structure information about conditions that existed in our galaxy long before the formation of our solar system. However, theoretical models suggest that objects forming directly from the interstellar medium would possess characteristics very different from those observed in 3I/Atlas, making this scenario difficult to reconcile with current observational evidence. Advanced statistical analyses attempt to constrain probable origins by examining the motion of 3I/Atlas relative to the known kinematic properties of different stellar populations in our galactic neighborhood. Objects ejected from young stellar systems should display velocity characteristics that differ systematically from those originating in older, more evolved stellar populations. The kinematic signature of 3Y/Atlas suggests association with the galactic thin disk population, relatively young stars that participate in the organized rotation of the galaxy around its central supermassive black hole. This kinematic evidence points toward origin from a stellar system similar in age and metallicity to our own Sun. But the precision of current measurements remains insufficient to identify specific candidate sources with high confidence. Professional astronomers conducting these origin studies find themselves confronting the fundamental limitations of backward trajectory integration over cosmic timescales, where even tiny uncertainties in initial conditions lead to exponentially growing uncertainties in calculated past positions. The cosmic detective work required to identify the source of 3I/Atlas pushes current observational and computational techniques to their absolute limits while demanding precision that may remain forever beyond reach. The investigation of 3I/Atlas's internal density structure unveils yet another layer of mystery that challenges fundamental assumptions about how solid objects should be constructed to maintain structural integrity while traveling through the hostile environment of interstellar space. Density measurements derived from various observational techniques yield results that seem to violate basic principles of physics and materials science, suggesting an object with properties unlike anything previously encountered in astronomical investigations. The determination of asteroid density typically relies upon careful measurements of both mass and volume, parameters that can be estimated through a combination of gravitational effects, thermal observations, and geometric constraints derived from photometric analysis. For objects that lack detectable gravitational influence on other bodies, researchers must employ indirect techniques that relate density to observable properties such as rotation rate, structural stability, and thermal behavior. Traditional approaches to density estimation for small solar system bodies have established that most asteroids possess densities ranging from approximately 1.5 to 5 grams per cubic centimeter, depending upon their composition and porosity. Rocky asteroids composed primarily of silicate minerals typically display densities in the range of 2 to 3 G per cubic centimeter, while metallic asteroids dominated by iron-nickel alloys can reach densities exceeding 7 G per cubic centimeter. Initial density estimates for 3I/Atlas, based upon its rapid rotation rate and apparent structural stability, suggest values that fall well below the range typical of known asteroid populations. The object's ability to maintain coherent rotation at periods approaching the breakup limit for gravitationally bound rubble piles implies either unusually high tensile strength or surprisingly low density that reduces the centrifugal stresses threatening structural integrity. Detailed analysis of the relationship between rotation period and density reveals that 3I/Atlas appears to operate in a regime where conventional models of small body structure become unreliable. The observed rotation rate should produce centrifugal accelerations that exceed the surface gravity of any object with typical asteroid density, leading to immediate disintegration through the ejection of surface materials unable to remain gravitationally bound. The apparent violation of these fundamental constraints forces researchers to consider scenarios that challenge basic understanding of how matter organizes itself on planetary scales. Perhaps 3I/Atlas possesses an internal structure dominated by large void spaces that dramatically reduce its overall density while maintaining sufficient cohesive strength to prevent rotational breakup. Such highly porous structures are observed among some solar system asteroids, where they result from incomplete gravitational reaccumulation following catastrophic collisions that shatter original parent bodies into fragments. The resulting rubble pile objects can possess porosities exceeding 50%, creating bulk densities significantly lower than the constituent rock fragments while maintaining marginal structural stability through weak gravitational and cohesive forces. However, the extreme porosity required to explain 3I/Atlas's apparent characteristics would exceed anything observed among known solar system objects, suggesting void fractions approaching 80 to 90% that challenge basic understanding of how such structures could remain stable over the extended timescales required for interstellar travel. The constant bombardment by cosmic rays and micrometeorites should gradually compact such loose structures, eliminating the void spaces that reduce effective density. Alternative explanations invoke the possibility that 3Y/Atlas consists of materials with intrinsically low density, perhaps dominated by organic compounds or exotic ice phases that remain stable under the extreme conditions encountered during interstellar travel. Certain classes of complex organic polymers can possess densities approaching those of water while maintaining structural properties that allow coherent behavior under rotational stress. Theoretical calculations suggest that objects composed primarily of such low-density organic materials could indeed display the rotational characteristics observed in 3I/Atlas without violating structural stability constraints. However, the formation of large objects dominated by organic compounds requires environmental conditions that remain poorly understood and may not occur naturally in most planetary formation scenarios. The possibility that 3Y/Atlas underwent significant internal modification during its interstellar journey adds another dimension to density interpretation. The extreme environment between stars subjects traveling objects to cosmic ray bombardment that can alter crystalline structures and create internal damage that reduces bulk density through the accumulation of radiation-induced defects and void spaces. Laboratory studies of materials subjected to high-energy particle bombardment demonstrate that such processes can indeed reduce bulk density through the creation of microscopic voids and structural modifications that persist over extended timescales. However, the degree of density reduction observed in these experiments remains insufficient to account for the extreme characteristics suggested by observations of 3I/Atlas. Advanced computer models attempt to reconcile the apparent density constraints with structural stability requirements through various combinations of composition, internal architecture, and evolutionary history. The simulations that successfully reproduce the observed characteristics require invoking object properties that approach the theoretical limits of what materials science suggests should be possible for naturally occurring structures. Some models propose that 3I/Atlas might possess a hierarchical internal structure with multiple scales of porosity, combining macroscopic void spaces with microscopic porosity in constituent materials to achieve unprecedented bulk density reduction. Others suggest that the object might be held together by cohesive forces stronger than simple gravitational attraction, perhaps through electromagnetic effects or exotic chemical bonding that allows stable structures despite apparent density constraints. The thermal behavior of 3I/Atlas provides additional constraints on its internal density structure. As the observed thermal properties depend critically upon the efficiency of heat conduction through the object's interior, highly porous objects typically display thermal characteristics that differ significantly from those of dense, coherent bodies due to the insulating effects of internal void spaces that impede heat transfer. The measured thermal response of 3I/Atlas suggests thermal diffusion properties that prove inconsistent with the extreme porosity required to explain its apparent low density through structural arguments alone. Objects with void fractions exceeding 80% should display thermal behavior dominated by radiative heat transfer through internal cavities, creating temperature distributions and thermal time constants that differ markedly from those observed. This fundamental inconsistency between density constraints derived from rotational dynamics and those implied by thermal observations forces researchers to consider that their basic understanding of the object's physical nature may be fundamentally flawed. Perhaps 3I/Atlas represents a completely new class of astronomical object with properties that cannot be understood through conventional approaches to small body physics. The accumulated evidence suggests that determining the true density of 3Y/Atlas may require abandoning traditional assumptions about how matter behaves under the extreme conditions associated with interstellar travel and formation in exotic stellar environments. The object appears to exist in a regime where conventional relationships between mass, volume, and structural stability no longer apply in predictable ways. Professional astronomers find themselves confronting an object that challenges not only specific theoretical models of asteroid structure, but also the broader assumption that all solid objects must conform to fundamental principles of materials science and structural mechanics. 3I/Atlas continues its journey through our solar system, carrying within its enigmatic structure secrets about the organization of matter that may require completely new theoretical frameworks to understand. The accumulated weight of observations transforms 3I/Atlas from an intriguing astronomical curiosity into a profound challenge to the theoretical frameworks that have guided planetary science for decades. Each new measurement adds complexity rather than clarity to the emerging portrait of an object that seems designed to confound every attempt at scientific classification. Displaying properties that individually stretch the boundaries of current understanding while collectively resisting integration into any coherent physical model, the failure of conventional theoretical approaches becomes apparent as researchers attempt to construct comprehensive models that simultaneously account for all observed characteristics of this enigmatic interstellar visitor. Models that successfully explain the object's thermal behavior fail to predict its rotational dynamics. Scenarios that reproduce its apparent density constraints cannot account for its spectroscopic properties. Frameworks that describe its outgassing characteristics prove incompatible with its observed brightness variations. This systematic breakdown of theoretical coherence forces astronomers to confront the uncomfortable possibility that 3Y/Atlas represents a type of object for which current scientific understanding remains fundamentally inadequate. The accumulated observational evidence suggests that conventional approaches to small body physics may simply prove insufficient when applied to matter that has undergone the extreme processing associated with millions of years of interstellar travel. Professional researchers publishing studies of 3I/Atlas increasingly resort to academic language that acknowledges the limitations of existing theoretical frameworks. Technical papers describe observations as inconsistent with current models, challenging conventional understanding, and requiring new theoretical approaches, right? Euphemistic admissions that the scientific community lacks adequate tools for interpreting this object's behavior. The interdisciplinary nature of the problems posed by 3I/Atlas becomes evident as investigators from diverse fields contribute expertise that proves individually insufficient yet collectively inadequate. Specialists in asteroid dynamics cannot explain the object's rotational characteristics. Experts in cometry physics fail to account for its outgassing behavior. Authorities on interstellar chemistry struggle to interpret its spectroscopic properties. Each subdiscipline brings well-established theoretical frameworks that have proven successful for understanding phenomena within their traditional domains. Yet none of these frameworks extends gracefully to encompass the hybrid characteristics displayed by 3E/Atlas. The object appears to exist in a liminal space between established categories, displaying properties that belong partially to multiple domains while conforming completely to none. The possibility that 3I/Atlas formed under physical conditions that do not exist within our solar system adds fundamental complexity to any theoretical interpretation. Different stellar environments create planetary systems with chemical abundances, radiation fields, and dynamical characteristics that can differ dramatically from local conditions, potentially producing objects with properties that lack terrestrial or solar system analogs. Theoretical models of planetary formation around stars with different masses, metallicities, and evolutionary states predict the creation of objects with compositions and structures unlike anything represented in our cosmic neighborhood. Such exotic objects might display physical and chemical properties that violate expectations based purely on solar system experience, requiring theoretical frameworks that extend far beyond current observational baselines. The extreme environment of interstellar space itself represents a largely unexplored regime for understanding how organized matter evolves over cosmic timescales. Objects traveling between stars experience conditions that combine near absolute vacuum with intense cosmic ray bombardment, extreme temperature variations, and complete isolation from planetary-scale gravitational influences for millions of years. Current theoretical models provide only crude approximations for how such conditions might modify the structure, composition, and physical properties of solid objects over the extended timescales characteristic of interstellar travel. Laboratory experiments that attempt to simulate these conditions necessarily operate over timescales that are many orders of magnitude shorter than actual interstellar journey durations, making it difficult to validate theoretical predictions through controlled studies. Advanced computer simulations represent the most sophisticated tools available for exploring how objects might evolve during interstellar travel. Yet, these simulations rely upon extrapolations of physical processes that have been validated only under terrestrial or solar system conditions. The computational models may fail to capture essential aspects of matter behavior under the extreme conditions that 3I/Atlas has experienced throughout its cosmic journey. The philosophical implications of 3I/Atlas extend beyond simple observational puzzles to challenge fundamental assumptions about the universality of physical laws and the adequacy of Earth-based scientific experience for understanding cosmic phenomena. The object serves as a reminder that the universe contains regimes where matter may behave according to principles that remain largely invisible to terrestrial investigation. Some researchers propose that 3I/Atlas might represent the astronomical equivalent of exotic matter predicted by advanced theoretical physics but never observed under laboratory conditions. Perhaps the extreme conditions of interstellar space allow the formation or preservation of material phases that cannot exist within the relatively benign environment of planetary systems, creating objects with properties that challenge conventional understanding of condensed matter physics. Alternative interpretations suggest that 3I/Atlas might simply represent an extreme example of conventional matter that has undergone evolutionary processes beyond the range of solar system experience. The object could embody perfectly ordinary physics operating under extraordinary conditions that produce extraordinary results difficult to recognize or interpret through conventional observational techniques. The accumulating evidence forces the astronomical community to acknowledge that some cosmic objects may remain permanently enigmatic despite the application of increasingly sophisticated observational and theoretical tools. 3I/Atlas demonstrates that the universe retains the capacity to surprise and humble human scientific confidence. Regardless of how comprehensive our theoretical frameworks appear or how precise our measurements become, The broader implications for astronomy and planetary science prove equally profound, suggesting that current understanding of small body populations may be severely biased toward objects that formed under the specific conditions characteristic of our own stellar environment. The true diversity of matter in the universe may far exceed what can be inferred from study of solar system representatives alone. Professional astronomers find themselves confronting an object that embodies the fundamental limitations of scientific inference based upon limited samples and localized experience. 3I/Atlas continues its journey through our solar system as a permanent reminder that the cosmos contains phenomena that may forever challenge human attempts at complete understanding. Regardless of how sophisticated our tools become or how confident our theories appear, the search for cosmic analogues to 3I/Atlas leads astronomers through comprehensive databases spanning decades of small body observations. Yet, this systematic investigation reveals the profound isolation of an object whose characteristics appear unprecedented in the accumulated archives of solar system science. The comparison process, which typically provides crucial context for understanding newly discovered objects through reference to similar previously studied examples, yields instead a deepening appreciation for just how extraordinary this interstellar visitor truly appears to be. Solar system catalogs contain detailed observations of hundreds of thousands of asteroids, comets, and small planetary satellites accumulated through ground-based surveys, spacecraft encounters, and space-based monitoring programs that span multiple decades of increasingly sophisticated investigation. These archives represent humanity's most comprehensive inventory of small body properties, encompassing objects that range from near-Earth asteroids just meters in diameter to massive main belt bodies hundreds of kilometers across. The diversity captured within these databases initially suggests that some previously catalogued object should display at least some characteristics similar to those exhibited by 3I/Atlas. After all, the solar system contains objects with unusual rotation rates, anomalous spectral properties, complex thermal behavior, and irregular outgassing patterns that individually resemble aspects of the interstellar visitor's behavior. However, systematic searches through these vast archives fail to identify any single object that combines even a subset of 3I/Atlas's most distinctive characteristics. Objects with rapid rotation rates typically display the high density, high strength properties expected for small, coherent bodies. Bodies with unusual spectral signatures generally conform to conventional thermal and dynamical behavior. Comets with anomalous outgassing patterns still develop obvious coma structures when approaching the inner solar system. The absence of close analogues becomes particularly striking when researchers examine the population of interstellar objects detected during the brief period since astronomers developed the capability to recognize such visitors reliably. 1. I/Oumuamua displayed its own set of unusual characteristics, including extreme elongation and mysterious non-gravitational acceleration. Yet its behavior proved far more amenable to theoretical interpretation than the systematic enigma presented by 3I/Atlas. 2I/Borisov, by contrast, behaved almost exactly as theoretical models predicted for interstellar comets, developing a conventional coma and tail structure while displaying spectroscopic and thermal properties entirely consistent with solar system analogues. Its predictable behavior provided reassuring confirmation that at least some interstellar objects conform to expectations based upon local experience. The stark contrast between these three interstellar visitors highlights the dangers of drawing general conclusions from limited samples, while simultaneously emphasizing just how anomalous 3I/Atlas appears within even this small population of cosmic wanderers. If interstellar objects are supposed to display properties similar to their solar system counterparts, then 3I/Atlas represents a profound violation of these expectations. Theoretical models of interstellar object populations predict that most such bodies should indeed resemble solar system analogues, differing primarily in composition due to formation around stars with different chemical abundances rather than displaying fundamentally different physical behavior. The models assume that basic physics operates consistently throughout the galaxy, producing objects that may be exotic in composition but familiar in their fundamental structural and dynamical properties. Extended searches through archives of unusual solar system objects identify several bodies with individual characteristics that might be considered precursors to the behavior displayed by 3I/Atlas. Some asteroids display remarkably flat spectra that resist compositional interpretation. Others exhibit thermal properties that challenge conventional models. A few show evidence for weak outgassing without obvious coma development. Yet none of these potential analogues combines multiple anomalous characteristics in ways that approach the systematic strangeness of 3I/Atlas. The interstellar visitor appears to exist in a category of its own, displaying a constellation of properties that has no precedent in the accumulated experience of solar system astronomy. The search for analogues extends beyond our immediate cosmic neighborhood to examine objects detected in other planetary systems through various remote sensing techniques. Exoplanet transit surveys occasionally detect evidence for small bodies in distant stellar systems, while direct imaging programs have begun to resolve debris disks and planetary formation regions around nearby stars. However, the observational techniques available for studying objects in other stellar systems remain far too limited to provide meaningful comparisons with the detailed characteristics observed in 3I/Atlas. Detecting the equivalent of an asteroid or comet around another star requires observational capabilities that exceed current technology by many orders of magnitude, leaving researchers dependent entirely upon solar system experience for comparative context. Theoretical investigations explore whether the extreme conditions characteristic of specific stellar environments might naturally produce objects with properties similar to those displayed by 3E/Atlas. Perhaps formation around certain types of stars creates small bodies with structural or compositional characteristics that lead inevitably to the anomalous behavior observed in this interstellar visitor. Computer models of planetary formation in exotic stellar environments suggest several scenarios that could potentially produce objects with unusual properties. Formation in the vicinity of massive. Radiation-rich stars might create bodies with heavily processed surface compositions. Development around metal-poor stars could yield objects with structural characteristics unlike anything found in our metal-rich solar system. However, none of these theoretical scenarios successfully predicts the specific combination of properties observed in 3E/Atlas. The models typically predict objects that differ from solar system norms in predictable ways that reflect their exotic formation environments. Rather than bodies that systematically violate multiple aspects of conventional small body physics, the failure to identify meaningful analogues forces researchers to consider that 3I/Atlas might represent a genuinely unique type of object, perhaps the result of formation processes or evolutionary pathways that remain entirely absent from our local cosmic environment. Such uniqueness would make the object a cosmic laboratory for studying physical processes that operate only under conditions far removed from terrestrial or solar system experience. Alternative interpretations suggest that appropriate analogues might exist within the solar system, but remain unrecognized due to observational selection effects that bias astronomical surveys toward objects with conventional properties. Perhaps the techniques used to discover and characterize small bodies systematically miss objects with characteristics similar to 3Y/Atlas, creating an illusion of uniqueness where none actually exists. The profound isolation of 3I/Atlas within the context of known small body populations serves as a humbling reminder of how limited current understanding of cosmic diversity truly remains. Professional astronomers find themselves confronting an object that embodies the possibility that the universe contains types of matter and organization that may forever remain largely invisible to scientific investigation based upon localized experience and limited samples. The gradual recession of 3Y/Atlas from the inner solar system transforms what began as an intensive observational campaign into a race against time, as Earth's most sophisticated telescopes strain to gather final measurements from an object that grows fainter with each passing night. The interstellar visitor follows the inexorable mathematics of its hyperbolic trajectory, moving steadily outward beyond the orbits of Mars and Jupiter, while astronomers struggle to extract every possible piece of information before it fades beyond the limits of detectability. The observational challenges multiply as distance increases and apparent brightness decreases according to the inverse square law that governs all astronomical photometry. Objects that appeared as readily detectable targets during their closest approach to Earth become progressively more difficult to observe as they recede into the outer solar system, requiring ever longer exposure times and more sophisticated image processing techniques to maintain adequate signal-to-noise ratios. Professional observatories around the world coordinate their efforts in an unprecedented international collaboration designed to maximize the scientific return from these final observations. The largest ground-based telescopes dedicate precious observing time to tracking 3Y/Atlas, while space-based facilities provide continuous monitoring that avoids the atmospheric interference and diurnal interruptions that limit ground-based studies. The Hubble Space Telescope conducts a series of deep exposures that push the instrument to its sensitivity limits, attempting to detect any changes in the object's appearance or activity level as it moves through regions of space where solar heating diminishes and surface temperatures drop toward the extreme cold characteristic of interstellar conditions. These observations represent some of the most technically challenging measurements ever attempted by the venerable observatory. Each new set of observations carries increased uncertainty as the object's apparent brightness approaches the threshold where systematic instrumental effects begin to dominate over genuine astronomical signals. Photometric measurements that once achieved precision of a few percent now struggle to maintain accuracy within factors of 2 or 3, while spectroscopic observations become increasingly dominated by noise that obscures any subtle features that might provide final clues about the object's composition or behavior. The thermal observations prove particularly challenging as 3I/Atlas cools toward equilibrium with the cosmic microwave background radiation. The infrared emission that once provided crucial constraints on size and thermal properties becomes progressively weaker and more difficult to distinguish from instrumental background noise and contamination by zodiacal light scattered from interplanetary dust. Advanced data processing techniques extract maximum information from increasingly marginal observations, employing sophisticated statistical methods to identify genuine signals within data that approaches the fundamental limits of current detector technology. Computer algorithms designed to enhance weak signals and suppress systematic noise become essential tools for maintaining scientific productivity as traditional observational approaches reach their practical limits. The final astrometric measurements attempt to refine orbital elements with sufficient precision to improve predictions about where 3I/Atlas might be located during future observational opportunities, should technological advances eventually allow renewed study of this enigmatic object. However, the accumulating uncertainties in position measurements make such predictions increasingly unreliable over extended time periods. Spectroscopic monitoring continues until the object's apparent magnitude falls below the threshold where individual observations yield meaningful signal-to-noise ratios. The final spectra show no dramatic changes from the frustratingly featureless characteristics that have marked 3Y/Atlas throughout its passage through the inner solar system, providing no last-minute revelations about its composition or nature. The search for late-developing outgassing activity intensifies as the object moves through regions where different volatile species might begin to sublimate or where changing thermal conditions might trigger previously dormant processes. However, these final searches yield only negative results that establish increasingly stringent upper limits on possible coma development or material ejection rates. Radio astronomy facilities conduct final searches for molecular emissions that might indicate ongoing outgassing activity invisible to optical observation. These sensitive measurements detect no evidence for the characteristic spectral lines that would indicate the presence of water vapor, carbon monoxide, or other common volatile species, maintaining the mystery of how 3I/Atlas manages to lose mass without producing detectable signatures of conventional outgassing. The diminishing brightness also affects efforts to monitor rotational behavior and search for any changes in spin state that might have resulted from asymmetric outgassing or other torques experienced during solar approach. The final photometric measurements suggest that rotational characteristics remain essentially unchanged throughout the object's passage, providing no evidence for the spin-up or spin-down effects that typically accompany active mass loss. As 3I/Atlas approaches the outer regions of the solar system, where solar heating becomes negligible and surface temperatures drop toward the extreme cold of interstellar space, the object begins its transition back to the dormant state it maintained during millions of years of travel between stars. Any processes triggered by solar approach gradually cease as thermal energy dissipates and the object returns to equilibrium with its cosmic environment. The final confirmed detection occurs as 3I/Atlas crosses the orbit of Jupiter, moving outward at a velocity that will eventually carry it beyond the gravitational influence of our solar system and back into the vast emptiness between stars. The object's apparent magnitude has dropped to levels where only the largest telescopes can detect it reliably, and even these observations require extensive image stacking and processing to distinguish the object from background noise. Theoretical predictions suggest that 3I/Atlas will remain potentially detectable by next-generation survey telescopes for several more years as it continues its outward journey. But such observations will likely yield only astrometric data insufficient to resolve the fundamental mysteries that have characterized this object throughout its passage through our cosmic neighborhood. The scientific community faces the sobering reality that many of the most intriguing questions raised by 3I/Atlas may remain permanently unanswered despite the application of humanity's most sophisticated observational and theoretical tools. The object carries its secrets back into the darkness between stars, leaving behind a legacy of observations that challenge fundamental assumptions about the nature of interstellar matter and the adequacy of current scientific frameworks for understanding cosmic diversity. Professional astronomers find themselves in the unusual position of having accumulated vast amounts of high-quality data about an object whose fundamental nature remains essentially mysterious. The final observations serve as a reminder that even the most intensive scientific investigation may prove insufficient to decode the secrets carried by cosmic visitors from truly alien environments. The departure of 3I/Atlas into the outer darkness beyond our solar system's gravitational embrace leaves the astronomical community with a profound sense of scientific vertigo. As if the universe has deliberately presented Earth scientists with an object specifically designed to humble human confidence in the completeness of current knowledge. The accumulated observations span months of intensive study using the world's most sophisticated instruments. Yet, the fundamental questions raised by this enigmatic visitor remain as mysterious as when it first appeared in the telescopic field of view of the Atlas survey system. The scientific legacy of 3I/Atlas extends far beyond the specific puzzles posed by its individual characteristics to challenge the broader epistemological foundations upon which modern astronomy has constructed its understanding of cosmic phenomena. The object demonstrated with uncomfortable clarity that the universe contains types of matter and organization that may remain forever partially opaque to scientific investigation. Regardless of how advanced our observational capabilities become, or how comprehensive our theoretical frameworks appear to be, professional researchers analyzing the complete dataset accumulated during the object's passage confront the unusual situation of possessing extraordinarily detailed measurements of phenomena they cannot adequately explain through existing theoretical frameworks. Every major observational technique available to contemporary astronomy was applied to studying 3I/8LES, yet the resulting data defies integration into any coherent physical model that successfully accounts for all observed characteristics simultaneously. The spectroscopic measurements reveal an object whose surface composition remains essentially unknown despite months of intensive study using the most advanced spectrographs on Earth and in space. The thermal observations suggest thermal properties that violate conventional understanding of how solid matter should respond to solar heating. The dynamical measurements indicate mass loss through mechanisms that produce no detectable signatures of conventional outgassing processes. Each individual mystery might be accommodated within existing theoretical frameworks through the invocation of exotic but plausible physical properties or evolutionary histories. However, the systematic combination of anomalous characteristics displayed by 3I/ATLAS resists explanation through any coherent set of assumptions about its composition, structure, or formation environment. The interdisciplinary nature of the challenges posed by this interstellar visitor becomes evident as specialists from diverse fields contribute expertise that proves individually sophisticated yet collectively inadequate. Experts in asteroid dynamics cannot reconcile the object's rotational behavior with its apparent structural properties. Authorities on cometary physics struggle to explain outgassing activity that produces no visible signatures. Specialists in interstellar chemistry find no precedent for the observed spectroscopic characteristics. The failure of conventional approaches forces the scientific community to confront fundamental questions about the universality of physical principles and the adequacy of terrestrial experience for understanding cosmic phenomena. Perhaps the extreme conditions characteristic of interstellar space permit the existence of material phases or organizational structures that cannot form or persist within the relatively benign environment of planetary systems. Alternative interpretations suggest that 3I/ATLAS might represent an extreme example of perfectly conventional physics operating under extraordinary conditions that produce results difficult to recognize through observational techniques developed primarily for studying solar system objects. The universe may contain regimes where familiar physical laws yield unfamiliar consequences that challenge pattern recognition based upon limited samples and localized experience. The philosophical implications extend beyond astronomy to touch upon fundamental questions about the nature of scientific knowledge and the relationship between theoretical understanding and empirical observation. 3I/ATLAS serves as a case study in the limits of scientific inference, demonstrating how even the most intensive observational campaigns may prove insufficient to decode the secrets carried by objects that formed under conditions far removed from terrestrial experience. The object's journey back into interstellar space carries with it the accumulated frustrations and fascinations of an entire research community that devoted extraordinary resources to understanding a cosmic puzzle that ultimately resisted solution. The negative results prove as scientifically significant as positive detections, establishing stringent constraints on theoretical models while simultaneously demonstrating their inadequacy for explaining the full range of phenomena exhibited by this enigmatic visitor. Future theoretical developments in astronomy and planetary science will undoubtedly incorporate the lessons learned from studying 3I/8LAS, yet the specific mysteries posed by this object may remain permanently beyond resolution. The universe has provided humanity with a profound reminder that scientific understanding advances through the accumulation of partial insights rather than through the achievement of complete comprehension. The broader implications for understanding interstellar object populations prove equally significant. suggesting that the small sample of cosmic visitors detected to date may represent only a tiny fraction of the true diversity that exists among objects traveling between stars. Each interstellar visitor displays its own unique combination of characteristics, hinting at formation environments and evolutionary processes that span a range of conditions far exceeding those represented within our local cosmic neighborhood. Advanced theoretical models attempting to predict the properties of interstellar object populations must now incorporate the recognition that such objects may display characteristics that violate expectations based purely on solar system experience. The universe appears to support the existence of small bodies with properties that challenge fundamental assumptions about how matter organizes itself under the extreme conditions associated with cosmic scale travel and formation in exotic stellar environments. The continuing search for additional interstellar visitors takes on renewed significance as astronomers recognize that each new detection provides irreplaceable information about cosmic diversity and the range of physical processes operating throughout the galaxy. Survey programs designed to detect potentially hazardous asteroids may serendipitously discover objects whose properties expand human understanding of how matter behaves under conditions that cannot be replicated within terrestrial laboratories. Professional astronomers studying 3Y/Atlas find themselves participants in a cosmic experiment designed by the universe itself to test the limits of human scientific understanding. The object serves as a permanent reminder that the cosmos retains the capacity to surprise and challenge scientific confidence. Regardless of how sophisticated our theoretical frameworks become or how precise our observational techniques appear to be. The silence that follows the departure of 3I/Atlas carries within it the weight of unanswered questions and the gentle recognition that some cosmic mysteries may be destined to remain forever just beyond the reach of human understanding. As the object fades into the vast darkness between stars, it takes with it secrets that challenged every theoretical framework and observational technique that Earth scientists could bring to bear upon its enigmatic presence. In observatories around the world, telescopes turn their attention to other targets. Yet the memory of this puzzling visitor lingers in databases filled with measurements that resist interpretation and research papers that document phenomena they cannot adequately explain. The universe has reminded astronomy that for all its sophisticated instruments and comprehensive theories, science remains a human endeavor conducted within the narrow boundaries of terrestrial experience and limited by the particular conditions that characterize our local cosmic environment. The gentle drift of 3I/Atlas into the outer solar system marks not the end of a scientific investigation, but rather the beginning of a longer conversation between human curiosity and cosmic mystery. Somewhere in the darkness beyond Neptune's orbit, an object continues its ancient journey between stars, carrying within its crystalline structure information about formation processes and evolutionary histories that may forever remain partially hidden from scientific scrutiny. The story of 3I/Atlas becomes part of the larger narrative of human exploration at the boundaries of knowledge, where each new discovery reveals as much about the limitations of current understanding as it does about the phenomena under investigation. The universe continues its patient instruction of Earth scientists, offering lessons in humility wrapped in the deceptive simplicity of reflected starlight and the mathematical certainties of orbital mechanics. As night settles over the observatories and the stars wheel overhead in their ancient patterns, the cosmos maintains its eternal silence about the secrets it holds. In that silence, there is peace, and in that mystery, there is wonder that will continue to draw human curiosity toward the darkness between worlds, searching always for the next cosmic visitor that might carry answers to questions we have not yet learned to ask.